In this segment, we'll start looking at the coding template for homework 5. So let's turn and look at the code now. Again, homework 5 is the transient heat conduction problem. And you'll notice some differences here in the main.cc file. One is that I've created this constant alpha, which is an input for the constructor for our FEM problem object. Alpha is to specify what Euler method we're using. Now again, alpha can range anywhere from 0 to 1. For the homework, you'll be doing it for alpha equals 0, 1/2, and 1. But other than that, the mesh generation is very similar than setup system and assemble system. However, now we also have two solve functions. We have solve steady, which solves our steady state problem, and then solve trans, which obviously is the transient solution. In your header file, you'll have a function that calculates the L2 norm of the difference between the steady state solution and the transient solution at a given time. And so I'm also outputting to the screen here some of those results of the L2 norms. There will be 4 L2 norms. It will calculate the L2 norm at time equals 0, 1,000, 2,000, and 3,000. And those are some of the results that we'll be using in the grading. Let's shift over to the header file now. Just as in homework 4, I've defined order and quadrule as global variables at the top here. Again, when you turn in your assignment, use order equals 1 and quadrule equals 2. But for your own edification, you can change that order and quadrule if you'd like. DL2, again, will take care of any order or quadrature rule. We'll scroll down and look at the declaration of functions and objects. The first 4 solution steps are the same, but then we have this solve steady. Then we have apply initial conditions. Since it is a transient problem, or includes a transient problem, we have to include initial conditions. And so you'll be defining those within this function. That function is called within the solve trans function itself. I now have 2 output results functions, one for the steady state result and one for the transient results. Notice for the output trans results, I have as an input an index. So that's just to distinguish between the output results for, say, time equals 0 and time equals 1,000. It just puts an integer onto the file name so that it doesn't overwrite the solution file. And again, now we have another L2 norm function again. So if you've missed that from homework 2, it's back. You'll notice here we only have the quadrature formula for a volume integral. Since we don't have any Neumann conditions, we aren't doing any surface integrals on this problem. You'll notice I have more matrices and vectors here than before. We have capital M, which is our global mass matrix. There is again K, and then we have a generic system matrix. That's because when you're doing the transient problem, you have to do a couple of matrix inversions to solve for example, the Vm plus 1. And so system matrix is a generic matrix that you'll be defining later on in the solve trans function. We also have D steady, which is the steady state temperature profile. D trans, which would be the transient temperature profile at Tn or Tn plus 1. V trans would also again be similar. It's the transient time derivative of the temperature at each node, either for time Tn or Tn plus 1, depending on what part of solve trans you're in. And then again, our vector F and RHS. RHS is a generic right-hand side vector similar to system matrix that you'll be populating within solve trans to solve for your Vn plus 1 vector. Okay. We also have this standard vector of doubles called L2 norm results. This is going to store the L2 norm at various time steps. And then alpha. Alpha is just the input from our constructor. Okay. Specifying again what Euler method we're using. So if we scroll down to the constructor, Again, you can see we're inputting alpha and storing that within our class variable alpha. And if we scroll down to generate mesh, this again is exactly the same as previous assignments, where again you just need to define the limits of your domain. Define boundary conditions will be very similar to previous assignments, very similar to homework 3, which was your previous heat conduction, your steady state heat conduction problem, except now you'll notice that I have two maps here, boundary values of D and boundary values of V. I actually skipped over those. Up higher up, they are class variables, class objects. And since we have these two fields that we're dealing with the temperature distribution, and we're dealing with the field of the time derivative of temperature. And so we have boundary conditions on both of those. The boundary conditions on D are 300 at one end and 310 at the other. They are fixed temperatures, so what does that tell you about the boundary conditions on V, which is the time derivative of the temperature? It tells you, of course, that the derivative of D would be 0 at those boundaries where temperature is fixed. Okay? So you'll be doing a similar loop to check where your node is to see if it is at a Dirichlet boundary. If it is at a boundary, you'll put that information into these two maps using the global node index, which is the same as the degree of freedom index for this scalar problem. And you'll pass in the prescribed temperature value and the temperature time derivative, which again we said would be 0 when you have a fixed temperature. All right. So that will take care of your boundary conditions. Again, setup system is very similar to previous problems. There's nothing for you to change here. Let's look at assemble system very quickly before we end this segment. This is going to be sort of a mixture of the previous two homework assignments, your heat conduction problem and using FE values in the linear elasticity problem. Again, we have FE values here. We're going to update the values, update the gradients, and the Jacobian, determinant of the Jacobian times the quadrature weight values. I've set up this variable rho, and that's the specific heat per unit volume. It's a constant that we'll be giving you in your homework assignment that you'll use to define M local and then to get your global mass matrix. All right, so let's move inside the element loop. And first we're going to be populating M local. Let me write out that integral for you here on the board. M local AB is equal to the integral over the element's domain of rho, which again is your specific heat per unit volume. Now potentially that could vary across the domain. For this homework problem we're keeping it as a constant, so I could pull that out of the integral. But then it's simply the basis function b, a times basis function b integrated. Okay, so this is fairly straightforward, and from your experience doing k local and f local, this should be pretty straightforward for you, pretty simple. Okay, so you'll edit that there to find that here. We scroll down and we have to create k local. This will be the same k local as you created in homework 3. The only difference is you don't have to worry about the inverse Jacobians, since using DL2's basis function gradients, we already have the gradient with respect to the real domain. So that simplifies our quadrature loops a bit. All right, so we have looping over A, B, the quadrature points, which again, all three quadrature loops are grouped into a single quadrature loop with DL2. Then we do I and J to perform the multiplication with our conductivity tensor, kappa. All right. We don't have a forcing function in this problem, so f local will be 0. And so we don't even bother in this assembly to to assemble F, our global vector. But you will be assembling K and M, very similar to previous assignments, right? The solve steady function acts very similar as the solve functions in previous assignments. The small difference that I've done is instead of applying our boundary conditions within the assemble system function, I've shifted it down to solve steady, okay? And within this function, we'll solve for the steady state solution, and we store that result within the vector d steady. Okay, so that's nothing new up to there. Up to this point, we haven't done anything, we haven't solved for anything more than what you've already solved for in homework 3, which is just a steady state heat conduction problem. In the next segment, we'll move on to looking at solving the transient solution as the time progresses.